Okay, guys. So I'm gonna try and explain the parity stuff that Abifazal's been talking about, and I know it's confused quite a lot of people. Um, so I'm just gonna explain it now. So let is let's shrink this down for now. I'll explain that in a second. So um, the first thing is, what is this parity thing, or like parity, uh, error detection, all this like stuff he's been talking about, right? Um, and he talks about Hamming distance and parity bits and error correcting codes, and it all just seems like a mess. But I'll be honest with you, it's actually pretty simple, and I will show you why right now. So we're going to imagine that we have one person there and we have one person here. And this is essentially the entire basics of this topic. This topic is called error correction. Um, and and it's literally very, very self-explanatory. This topic is about correcting errors. So let's think of it this way. So this is a game of Chinese whispers. So um, so let's say the first person starts with dog, right? That's their word, and the kind of train of the thing, the train of the game goes along the entire game, and the last person comes out with the wrong word. Um, and this becomes very confusing because obviously what the sender, which is what we're going to call the first person, sent, and what the receiver, um, what the receiver received, um, are two different things, right? And that's because there's been an error along the way. So how do we fix this? How do we fix the errors happening? Um, and that's the entire concept. That's the entire like concept that we're learning at the moment. Um, so if we start very simply, um, and if you think about it for a second, without the sender telling the receiver, so at the end of the game, that the word they have is incorrect, there is no way that the receiver actually knows that the word that they have is wrong. They don't know it's wrong because, as far as they know, this is what they heard, right? Um, and in the middle of all this noise and people talking, this is what they heard. And until the sender tells them, no, this is the correct answer, it's dog, not dick, um, they think this is correct. So, how do we make it so that the receiver knows that the word they have is incorrect? So how can the receiver know that they have an error without the sender explicitly saying? That's the basics of error correction. So we're just going to put this in a little bubble here. I'm just going to make it a bit smaller and put it to the side. So just keep that in mind. So the way we do that in computer science is using something called parity bits. So in computer science, this is a word. So 1100 would be a word, right? Even though it's a binary number, it's known as a word. And each separate digit in this word is known as a bit. So altogether, you could say that this was a 4-bit word, right? Probably should write that 4-bit word. This is a 4-bit word, and that's because this word has 4 separate digits in it. And each of these bits will be transferred across. So like you can see in this rainbow chain, that arrow that I've drawn, this is dog is a word, and it's transferred and it comes out wrong. So how does the receiver know that there's been an error? That's what we're going to explain now. So let's draw a little diagram. So I'm just going to expand this one that I put down there earlier. Okay, so we have our sender and we have our receiver. And let's say this is the word that the sender wants to send. And the sender sends this 11-digit word across to the receiver, and the receiver wants to know if this is correct. And the way they do it is by checking something called parity. Parity in computer science is a way of like a checking method. And the way we do it in computer science is even parity is good. So even parity is good, and odd parity is bad. We don't want odd parity. And the way we check even and odd parity is we check when the receiver gets the message, is there an even number of ones? If there's an even number of ones, then this thing is... Oh, if there is an even number of ones, then it's even parity, and the receiver will say, okay, this message is good, it's not corrupted, it's not wrong, we're completely fine. If there's an odd parity, however, if there's an odd number of ones in the receiving message, then the the receiver will know, oh, there's something wrong, I need to fix this error. And we're going to learn about the simplest method of fixing errors, which is called Hamming code. So if we scroll down again, and I'm gonna, I'll move this thing down a bit. Oh Jesus. Sorry. Okay. Actually, I'll just shrink this again. So if you note this down, that even parity is good and odd parity is bad in computer science generally. So we have our sender and receiver. I'm gonna make them. I'm gonna turn them to S and R. S and R. And our sender sends this number. So 0 0 1 1 0 0 0 1 1 1 0. And for the receiver, when the receiver gets this message, they want to know that this is correct. So obviously when we're sending, I said that even parity is good and odd parity is bad, and parity is the number of ones. So if we count the number of ones here, we have 1 2 3 4 5, and that's odd parity, which is bad, right? So if the sender has odd parity, then that when the receiver gets it, it looks like there's a mistake. But in reality, there is no mistake, because this is exactly the message that the sender wanted to send. So it's up to us to make it so that this sent message has an even number of ones. And the way we do that is by adding what we call parity bits. And parity bits are, if you remember, I said each digit is a bit. Parity bits are extra numbers we'll add into the message. So these won't necessarily be at the end. They're usually like spread out throughout the entire thing, and I'll explain that in a second. And what these will do is make it so that there's now an even number of, for example, ones when you're sending it. So now there's 1 2 3 4 5 6 ones. Receiver will look and say, oh, we got 6 ones, that's nice. The code is okay, there's nothing wrong with it, this is the correct message. But these parity numbers also serve a different purpose. They make it so that when the receiver gets it, if there is an error, for example, the receiver can pinpoint exactly where that error is just using these numbers here. And if you've never seen it before, it really seems like magic, because the cool thing about parity is that it scales really well. So, for example, if I have a 256-bit word, so that is massive, try and take a guess in your head at how many parity bits we're going to need to add, so that the receiver can check any errors and make sure the code is correct. You'd think that you need quite a few, right? But actually, you only need 9 parity bits. For a 256-bit word, you need 9 parity bits to make sure the entire thing is correct. And that's really powerful, because what that means is you now, instead of having to maybe make a backup of the word when you send it, which will obviously double the file size that you need to send it in, you now only need 265. There we go. Now you need a 265-bit word, including the parity bits, and now the receiver can check and see that the message is correct, right? And it's a very efficient way of doing things, and it's the oldest way this was made. But before we start, we need to understand a few restrictions of this method. So this method is adding parity bits that the receiver can then decipher is called a Hamming code method. I'll just write that there. This is called Hamming code, and is the first method of error detection ever created. But there is a problem with it, because let's say we have an error, right? And this error is, so let's say this is our code, this is our parity bits, we're not going to touch them. So right now there's 6. 1, 2, 3, 4, 5, 6. So let's say we have one error. So a 0 is flipped to a 1. Now we have 1, 2, 3, 4, 5, 6, 7. And now the receiver knows that's an odd parity, which is bad. And it can look for it, find it, and correct it. But now, let's say this happened. We have parity that's right next to each other. So we have things that are being flipped right next to each other. So we have now 1, 2, 3, 4, 5, 6, 7, 8. 8 ones, which is even parity. So the receiver thinks, oh, that's cool, I've got even parity, there's nothing wrong, the code is fine, I can send it off. When in fact, it's actually wrong, right? And this is a big problem, and the most the most significant problem with the Hamming code method. In information transfer nowadays, we use a much more sophisticated method. We've even started using like quantum error detection, which is really cool. You can look that up if you're interested. But this is like the oldest method we're learning, and it's probably the simplest, which is why we're learning it. So that's the limitations. So if you're asked for the limitations of this method, so limitations, you would write that it can only detect, it can only correct one error, but it can detect 2 errors, but it can't correct any of them. Can't correct them. I apologize for my horrible handwriting. It can't correct them. So these are some big limitations of the Hamming method. And I'm just going to we'll go back to this once go back to this once I've shown you how to do this stuff. Apologize for this slowness. Excellent. Okay, so at least we can get back up here. Okay, so you can detect 2 errors, but you can't correct them. Now we're gonna go back to our sender and receiver one more time. So we have our sender here and our receiver here. We have our word here. So 0 0 1 1 0 0 0 1 1 1 0, and we have our receiver here is receiving the message. Now, a big question is, how do you know, and where do you add the parity bits? So I said earlier, that the parity bits aren't all stacked at the end or all stacked at the front. They're spread out through the entire code. And the way we can find out where they are is we're actually going to number these. Give me a sec. There we go. There we are. We're going to number the positions of this. Okay. So the 0. So the first letter or the first position is always a 0th position, right? The second position is the first. So in programming, you always start with 0. So 0 is the first element. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 0 to 10 when you're doing a programming count. But you know it's 11 elements because you just add 1 to the end, because I told you this was an 11-bit word. So you just add 1 to the last thing, and you can see how many elements it is because we start at 0. And what parity bits, as I said, they help the receiver detect where the errors are. They appear at every power of 2. So they appear at 2 to the 0, 2 to the 1, 2 to the 2, etc, etc, etc. So here they would appear where the 0 is now, so I'll just actually highlight them. So they would appear here. They would appear 2 to the 0 is 1. They would appear at 0. We'll talk about that in a sec. 2 to the 0 is 1, so it would appear at the first position. 2 to the 1 is 2. It'll appear at the second position. So 2 here. 2 to the 2 is 4. It'll appear at the fourth position. 2 to the 3 is 8. It'll appear at the 8th position. 2 to the 4 is 16. If it was 16, it would appear at the 16th position, etc, etc, etc. So the way you determine how many they're called parity bits. So each of these positions, so remember I said 1 digit is called a bit. So each of these positions is a bit. So 1, 2, 3, 4. Is you look at the number of elements, so 10, and you look at the power of 2 that's the next smallest to it. So for 10, the power of 2 above it is 2 to the 4, which is 16, and obviously 16 is greater than 10, so it's not necessary. But if you look below it, 2 to the 3 is the smallest that's closest to 10, so you would take 8. And the way parity bits work are you would add them into your word. So for example, the first element would be a parity bit, so let's say 0. The second element, the 0th position would be a parity bit. The first position would be a parity bit, so I'm just going to put numbers there, random numbers. The second position would be a parity bit. 3, all right, 3. The third position would just be a normal number, so we can put we'll put the first. We'll write this number in order, so it'll be the first letter of this, the first bit of this number should be 0, and then the fourth position is a parity bit. The fourth position is a parity bit. Ignore the numbers in green. I'm just showing where the position of the parity bits will be. So 1. and then the 5th, 6th, and 7th will be normal numbers. So it would be 0. So we wrote 0. So the next 3 numbers 0, 1, 1. And then the 8th position would be a parity bit, and then everything else would just be a normal number. So it would just be 1, 2, 3, 4, 5. Yeah, that's right. So you'd go where have we written it? We've written up to 0, 0, 1, 1, and then 0, 0, 0, 1, 1, 1, 0. I think the last one is a parity bit. I just need to check real quick. 1, 2, 3, 4, 5. So 20. Yeah, okay. No, we're good. I think the last one is a parity bit, I believe. Okay, so 2 to the 4. So okay, so if we look at the positions here, I'm going to draw them in red so we don't get confused. So this is the 0th position, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9, 10, 11, 12, 13, 14, 15. Yeah, we don't need another parity bit. So so you can see here, you have a parity bit at the 0th position, the 1st position, 2nd position, 4th position, 8th position, and there's no like power of 2 above that. If there was a 16 here, you would have needed. If there was one more here, you would have needed an extra bit. So now you can see this 11-digit 11-digit word has become a 16-digit word. But now, even though it's a bit bigger, what it allows us to do is... Sorry, I'm just going to move this up a bit. Even though it's a bit bigger, what it allows us to do is it allows a receiver now to check for any errors that might have occurred in the transmission. And that's where this thing comes in. So let's look through what you know at the moment. So you have your sender, which is S. You have your receiver, which is R. You have your word that the sender is sending, which is 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. It's 21 bits long. So it's a 21-bit word, right? And for those of you who are slightly more perceptive, you'll notice that some of these are outlined in bold, and if you look at the position of them, so whenever we're counting this for error detection, we'll count from the right to left. So whenever you count in binary, you count from right to left. So if you note the positions of each of these, each of the like bold bits, you got 0, 1, 2, 3. They've started counting from 1. Stupid things. 1, 2, 3, 4, 5, 6, 7. Technically, it should be 0, but apparently this is how Abo Fazl does it. But he's confused people, so he starts counting from 1. I think he might have forgotten, because usually you would start from 0. I think he's done it for the ease of most people, just because you're used to counting from 1, or maybe he forgot because he was like half asleep when making his lecture notes. But you know, who knows? Anyway, so at the first position, look, we have a bold. The second position, look, bold. Fourth position, bold. Eighth position, bold. 16th position, bold. See that? Does that link up with anything that I've told you? Yes, it does. Those are the positions of the parity bits. And, you know, that's what you know so far. Now, let's take a look at this massive table under here that I've gone and highlighted for you. What this is just like... The easiest way I can think of explaining it is if the people who are comfortable with logic gates, when, let's say you have a logic gate with 3 inputs, A, B, C, and then F is your output. And you want to record all the inputs. You want to record all the inputs for these 3, right? So obviously you'd have 8 inputs because there's 3. You'd have 8 combinations because there's 3 inputs, right? So you would go, how would you do it? You'd go 0, 1, 0, 1, 0, 1, 0, 1, and then you go 0, 0, 1, 1, 0, 0, 1, 1, and then you'd go 0, 0, 0, 0, 1, 1, 1, oh, 1, 1. And that'll give you every combination, right? And like that's it's the same thing. It's kind of boilerplate. That's what this graph is. It's pretty much the equivalent of this. So if you look here, so each of these, I'm gonna put like a dot next to it in green. Actually, I highlight it in green. No, that's confusing. I'll put a dot next to it in green. So each of these refers to the position of the position of where the what was the name again? Keep forgetting. Parity bits are. So 1 is the. I should probably know that. 1 shows that in the first position you have a parity key. 2 says that in the second position you have a parity key. 4, 4th, 8, 8th, 16, 16th. That's what these mean. So if you look at what I've done here, I've gone 0, 1, 0, 1 and then 0, 0, 1, 1. I did the same thing here. Look, I go X miss. So if we say X miss, X miss, X miss, X miss, X miss, etc., etc., etc. So you just keep on going like that. And then the second one, you'll see, I'll explain this gap here later. You'll see you go X, X, miss, miss, X, X, miss, miss, X, X, miss, miss, which is what I've done here, 0, 0, 1, 1, 0, 0, 1, 1. And the last one, and then the next one is, ignore this gap here. It goes X, 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 miss, 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 X, 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 miss, 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 X, X, and then it stops because there isn't more places for the X's to go. And it's exactly the same thing that I've done here. And it just goes on for bigger and bigger numbers, right? Because this is 8, then a miss of 8. Well, not quite a miss of 8 because there's not enough space, but it would be. But you'll notice that at the front here, there's gaps, right? So there's gaps here, there's gaps here, and there's a massive gap here. And you might ask, well, Addy, those don't follow the pattern. You've not told us that. So the reason for that is because if you look, so for example, if we take number 2, so the second parity bit, if we look at this gap here, it's already been covered by 1. So if you look above it, you'll see it's already been covered by 1. So the way I think of it, each of the parity bits kind of controls other bits in the entire word. So the first bit controls every like odd bit in the word. The number 2 controls 2, 3, 6, 7, 10, 11, 14, 15, so on and so forth. So this is already controlled by X. So 2 does not need to. These X's are called flags, by the way. 2 does not need to flag this. I'll write that here. Flag. 2 does not need to flag that, and equally so. Equally so, like if you look at 4, if the fourth parity bit, if you look at the parity bit in the fourth position, x is covered by, it's already flagged by yellow here, it's flagged by green here, and it's flagged by green and yellow here, so it doesn't need to check it. Then it starts on the one that's empty, that's not covered by either of them. Same goes here. This is covered by yellow, by green and yellow. This is covered by blue, but then in this column, nothing is covered. So this is the first one that 8 will start on. And then if you look at this, this is covered by yellow, green, blue, all of this. And then purple covers all of these. And then if you look here, in this column, the 16 column, nothing is covered by any of the parity bits here. So then 16 will start there. So all this is showing, all this like kind of graph in the middle is showing, is which bits do these parity bits kind of control, if you will. And he hasn't done a very good job of explaining it, I'll be honest with you. But that's all this means. And then R is the result. So I am going to... I don't want to draw out the entire thing. I'll show you what he's done here. Establish even parity with Biddly Biddly. So what he's done here is he's saying, well, let's assume what he's saying is, let's assume that the result that we're given, we know that in the result that we know that this bit here has been flipped, right? He's saying we're going to assume that, right? So he says bit 5 flipped between sender and receiver. So you'll see this word here at the bottom that the receiver has is a copy of the one the sender has, apart from this bit, which is obviously flipped. So if you look there, this bit has been flipped, right? And he's saying, let's assume the receiver is given that bit and it's flipped. Okay, so let's write that out. So let's say we're the receiver, and we're given 0, 1, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0. So this is the result that we're given. And okay, so if I scroll down here, you don't know which one's errored, right? And I'm just going to go and highlight the parity keys. So this is parity, this is parity, this is parity. 8 was 8. This is parity. And this is parity. So one's first position, second position, fourth position, 8th position, 16th position. So as a receiver, this is the number that we get. And we don't know this number, if this number is like correct or incorrect, or what errors have happened to it. And what Abufazel is trying to say is, how do we check for this? How do we check if this is incorrect? And he's shown here that this 0 has been flipped. But obviously, if you receive something, you won't know it's incorrect until the sender tells you. So how do you check without the sender telling you? Well, you use the parity keys. How do you do that? So, do you remember here I said each of these will control, each of these like parity bits will control other bits in the code. Okay, now I'm going to show you something cool. Let's take a look here. So what Abufazel has done, he's written the first row out by himself, and he's put all the x's, so x space x space x space x, like the pattern that I told you before. And in the first one, so this is the first parity bit, he's gone through and written in the relevant letters, the relevant the relevant bits for each for the like corresponding values of those x's. So if you look at the x here, he's written down a 0 because it's in the same kind of column. He's written down the bit in the third position. He's written down the bit in the fifth position. He basically the bits that correspond with the positions that the x's are in, he writes down. And you'll see that he like misses out a lot that are not written in here. So for example, he misses out every other one in this example, and the reason for that is because he's only checking for the values that have x in them. So he'll write down 0 1 0, and that's the one that's been flipped. 1 0 0 1 1 0 1 0. Okay, I feel like I'm Abufazel now. And basically this is trivial. Using your intuition, you can see this is 0 0 0 0 0. Anyway, so what we're checking for is we're checking for parity, right? So we have 1 1, 2 1s, 3 1s, 4 1s, 5 1s. And now if you remember, 5 1s is odd parity, which is bad. So this is bad. So you can see here, he makes this one row red because he knows there's an error there. Something's gone wrong. Then he does the second row, so test bit 2. So he tests the parity bit that's in position 2. So he does his pattern. Remember, he skips this first box because it's already controlled by the first parity. So he skips that, then he does 2, skip 2, 2, skip 2, 2, skip 2, 2, skip 2, 2. And he writes the numbers that are in the bits that are in the same position as the x's. So he'll go, this 0 is in the second position, this 0 is in this x's position, this 6 is in this 1 is in this x's position, this 1 is in this x's position, so on and so forth. So whatever bits correspond with the place where the x is, he'll write them down. So if we look here, I'll actually write it out for you. So we have the positions of the x's here actually. So there. So I'm gonna write them out in. Let's go for plum. So we miss out this one. So we don't care about this one. We write out these two, so that's 1 and 0. He misses out this one, and he misses out the next one, and then he writes 1 and 1. Then he'll miss out this one, and he'll write 1 and 1. He'll write 0 and 0, because these are the ones. He'll miss out these two, so these two missed out. These two are missed out. Yeah, fucks it up. Alright, let's start again from the top. So, this one is missed out because, this first one is missed out because the one already controls it, right? So, that's missed out. I'll put an underscore when it's missed out. Then he'll write in the next two ones, so 1, 0. And then he'll miss out the next two, so miss, miss. And then he'll write in the next two. And then he'll miss out the next two. He'll write in the next two. You can see how the pattern is going on. Then he'll write out the next two. And he'll miss out the next two. And he'll write out the next two. And then he'll miss out the next two. So in the end, you'll get something that looks like this with like gaps here. So 2 gaps between each one. And when you look at what he's written, it's 1 0 1 1 0 0. Oh shit! I don't know why I wrote 1 1 there. 0 0 1 0 1 1 positions match. Yeah, you see that? Um, this is the most confusing bit of the like the entire thing. So if you don't get it, like put it in the comments or just ask me in the chat or whatever. And if you count the number of ones here, you have 1, 2, 3, 4, 5, 6. That is even parity. Now, even parity is good. We're happy with even parity. And we go into test case 4, and we put in the values corresponding to the place where the x's are, and we get 0, 0, 1, 1, 0, 1, 0, etc. And then you count the number of ones there are. So we have 1, 2, 3, 4, 5 ones. Now 5 is bad parity, so we flag up 4. So 1 and 4 are flagged up. Then you test 8, and 8 has 1, 2 ones, so it's an even number of ones, so that's good. So that's okay. And then we go into 16. 16 has 1, 2, 3, 4, which is even, which is good. So 16 is okay. Now, the way we do it is after we've checked everything, we now have this situation. We know that rows, so rows 1 and 4 have odd numbers of ones. I'll write those in like that. So have odd numbers of ones, right? And that's bad. So they were flagged. So they were flagged. And to find the bit that's errored, to find the error bit, you do 2 to the power of both of these. You do, and I'll write this out slightly neater. You do 2 to the power of the first row that's errored, which was, if you look here, 1 was the first row that errored. So 2 to the power 1. And then you add it to this other row that's errored, which is 4. 2 to the power 4. And because both of these have errored, you add 2 to the power 1 plus 2 to the power 4 together. No, wait. Do you do that? Oh, no, you don't even do that. My apologies. You just add 1 and 4. You get 5. And now you know that it's the 5th bit that has errored. So the 5th bit has errored. So now you know that. You can just go back, see where the 5th bit is. Remember, you count from the right. So you'll count. I'll just rub this out because that's confusing. So you'll find where the 5th bit is. So you go. So that's 1. So you go. This is 1, 2, 3, 4, 5. This is our 5th bit. The 5th bit has errored, so all you're going to do is you're going to change it. You're going to change it to 1, which is the correct value. And that's how you know something is errored. That's it. That's literally it. So that's how you know stuff is errored. I haven't done any of this, but I've covered 11 out of 19 pages. So that's slightly more than half the material. So hopefully that has, explain stuff a bit more. And yeah, good luck.